Okay, ladies and gentlemen, this is the video where I'm going to go through some specific examples of using K to determine concentration that apply to Ka. I'm going to talk about Kb and then Ksp. So this is we've already watched the first video, we understand the idea of the approximation, we understand using X in our ice chart, and now we're going to look at this in the context of specific acid-base chemistry or solubility chemistry. I will say right now that while the AP has on occasion asked an equilibrium question that is not Ka, Kb, or Ksp, it is much more common for them to couch their equilibrium problems within the context of acid-base chemistry and solubility chemistry. So you are very likely to see either Ka, Kb, or Ksp questions being asked about equilibrium. And you are going to be expected to do these types of problems in problem set number 3. So our first example problem, using Ka to find pH. What is the pH of a 0.3 molar solution of acetic acid at 25 degrees Celsius? Ka value for acetic acid given, 1.8 times 10 to the minus 5th molar. This is such a standard equilibrium problem. This is probably the most common type of equilibrium question that exists out there. This one right here, determining pH from a Ka value. This, hopefully by the end of this unit, you feel very comfortable with doing this type of thing. It's super common. It's probably, in terms of equilibrium problems, pretty straightforward, and this is definitely something we have to feel comfortable doing. So what are the 3 steps to solving an equilibrium problem? Number 1, we want to write a reaction if 1 is not given, and oh look, 1 is not given. Number 2, we want to fill in an ice chart. Number 3, we want to take the stuff from our ice chart and plug it into the equilibrium expression. So write reaction, fill in ice chart, go to the equilibrium expression. So we want to write a reaction. Well, what reaction are we going to write? There's a major tip-off to you in the question itself that tells you what reaction to write. And it's right here. The fact that they give you a Ka value means that you have to write a Ka reaction, because it goes with that particular value. If Ka is given, you write a Ka, meaning an acid dissociation reaction. If Kb is given, you write Kb, base dissociation reaction. If you're given Ksp, you write a solubility dissociation reaction. So that's really your big tip out. What reaction am I writing? What's going on here? I mean, the only thing that's in solution is acetic acid. So we want to write a reaction that shows acetic acid acting like an acid. So acetic acid, that's one that we have to know. Acetate ion, C2H3O2 with a charge of -1. So acetic acid is going to be H. C2H3O2. Now this is an acid dissociation reaction. What do acids do? They donate protons. So we want to write that dissociation for that H plus coming off and being left with nothing but the acetate ion that remains, C2H3O2 minus. So that's our first step. We've written a reaction to describe what's going on in this solution. Secondly, we want to fill in an ice chart, and that's why we need a reaction, right? You can't fill in an ice chart unless you have a chemical reaction. So now we're going to fill in initial concentrations. The only initial concentration that we've been given directly is this 0.3 molar of acetic acid, so that's okay. 0.30 molar goes in our initial spot for our acetic acid. Now we have indirectly been given the initial concentrations of the H plus and the acetate ion because no information in the problem has told us that we are starting in our little beaker with any H plus or acetate. There's absolutely no mention of it, which means we are assuming that we start with 0 product. But those are the only concentrations we have. We have Ka, but that's just a ratio of products to reactants. That's not a specific concentration. And we have temperature as well, but that's more just an indication that we're allowed to use that Ka value because it is tied to that particular temperature, which means we are now going to start using X's, that we do not know any additional concentration information, so we're going to use X to indicate our changes. We're going to say that our acetic acid decreases by X. And then we're going to use stoichiometry to say that if our acetic acid goes down by X, we have a 1 to 1 to 1 relationship here in our balanced chemical equation. So our H plus has to go up by X, and so does the acetate ion, right? 1 to 1, if we decrease by a certain amount for the acetic acid, we must increase by the same amount for the H plus and the acetate. Then fill in our equilibrium portion of the ice chart. So this is going to be 0.3 minus x. This is going to be x, and this is going to be x. But before we go any further, before we go on to the next component, going to our equilibrium expression, I'm actually going to make the assumption right now. Now remember, if k values are significantly less than 1, and typically we consider about k being on the order of 10 to the negative 4th to kind of be the cutoff for anything greater than that, and it's not significantly less than 1, anything less than 10 to the negative 4th, and it is significantly less than 1, well, this is less than 10 to the negative 4th. This is 10 to the negative 5th. That's even less than 1. So we can make the assumption that x in comparison with the starting amount is negligible. And I'm actually going to make that assumption right here in my ice chart. You can do it right there. You don't need a separate line. You can say, all right, 0.3 minus x is approximately 0.3. You do need to show that if you're making the assumption, which means that now we can go to the Ka expression, products of a reactants raised to their coefficients. So just having a look at the acid dissociation reaction. Our Ka expression is H plus times the acetate ion. These are concentrations, make sure we're including charges, divided by the concentration of acetic acid itself. So that's our Ka expression. We're now going to use what we know from the very last line of our equilibrium of our ice chart, in addition with the fact that the Ka value is 1.8 times 10 to the negative 5th. We're just plugging in. So we're going to do x times x over 0.3. And then it's simply solving. You're completely capable of solving for x at this point. We're just cross multiplying, and then we're going to be taking the square root. So when we solve for x from here, we get a value of 2.3 times, or 2.32 times 10 to the minus 3rd. Right, so that simply comes from solving the equilibrium expression where we've plugged everything in. Now looking back at our ice chart, and what does x represent? X represents the concentration of H plus at equilibrium, and it represents the concentration of the acetate ion at equilibrium. Which one are we interested in? That's where we go back and to see what the original question was actually asking. So if we have a look at the question, it says, what is the pH? That's what we're looking for. So which of these two are we more interested in? We are way more interested in that one, because that's how we're going to get our pH. So we know then that our H plus is 2.32 times 10 to the minus 3rd molar, and from that we are getting our pH. pH is the negative log of our hydrogen ion concentration. So we're going to do the negative log of 2.32 times 10 to the minus 3rd molar. Doing that math, we get a pH value of 2.63. A quick comment before I talk about the check, because we do have to do the check. I haven't forgotten. But the reason that we cannot simply find pH by taking the negative log of that initial acetic acid concentration, that 0.3 molar, why we can't just take the negative log of that is because of this right here. That acetic acid does not completely dissociate, meaning if I have 0.3 molar acetic acid, I do not have 0.3 molar H plus. Only part of it dissociates, only a component, only a small percentage dissociates. And I have no way of knowing what that percentage is unless I work with the equilibrium constant. That's essentially what the equilibrium constant is describing. It's describing the ratio of products to reactants. So it's telling you, if you start with 0.3 molar, just how much product can you get from that. You can't get 100% dissociation, not from a weak acid, but it's talking to you about the a ratio that you do get. So that's why you have to do this as an equilibrium problem, and you cannot simply do the negative log of 0.3. That will not give you an accurate pH, not even close. So we've answered the question, but we do have to finish up, because as I said, you have two trade-offs for using the approximation and thus avoiding the quadratic equation to solve. You have to indicate that you're making an assumption, and then you have to check your assumption at the end. So for the check, we want to do part over whole. So the part was our x, basically what you solved for. It's always going to be your x. So it's 2.32 times 10 to the minus third. And then we were comparing that with that 0.3 molar. And what we were saying was that when you do that comparison, when you subtract the x from 0.3, it's still approximately 0.3. When you do this math out, I get a percent dissociation of 0.77%. We want it to be less than 5, which it is, so our assumption is valid, and it's okay, and we don't have to go back and reevaluate the math. 0.77% dissociated. Acetic acid is one of the stronger weak acids that's out there. That's how quote-unquote weak acids truly are. I mean, if acetic acid is at the strong end of the spectrum, and it's really not that strong, it's less than 1% dissociated. That's why there's such a massive difference between our strong acids and our weak acids. So the next thing is using Kb to find pH. Now, I'm not going to go through this problem completely. What I am going to do is kind of set it up, because basically all Ka and Kb questions really mirror one another really, really well. There are just a few key differences, basically the distinction between acid and base, but the process is very, very similar. The few things to sort of note: when you're doing Kb problems, X is not going to be H+, X is going to be hydroxide, because based on the reaction that you're writing, which you'll see in a second. So you have to be aware of that if you're looking for pH, which you probably are. It's much more common to get asked about pH, even for a base problem, than it is to get asked for straight up pOH. So you have to be mindful that your X is no longer representing the hydrogen concentration at equilibrium, but the hydroxide concentration of equilibrium. So this problem, I'm not going to go through all the math, but I am going to sort of set it up and get it started. Determine the pH of a 0.2 molar solution of ammonia. The Kb of ammonia is 1.8 times 10 to the minus fifth. No, I actually have not made a mistake. The Kb value for ammonia is actually identical to the Ka value for acetic acid, which I always find kind of funny, because ammonia is probably the most common weak base that we work with, and acetic acid is probably the most common weak acid that we work with, and they have the exact same equilibrium constant values. Things that Mrs. Julian is amused by. Like I said, I was never cool, but I have these numbers memorized because we work with them a lot. So setting up this problem, step 1, write a reaction. So this is Kb, so it's base. So you want to write a base dissociation reaction. In order to do that, you have to add water, remember, to a base, because what do bases do? Bases accept protons by definition, so we're writing our base dissociation reaction. Next thing that we need to do, we need to fill in our ice chart. First thing that I'm going to do, cross off the water. Water is a liquid. Liquids are not included as part of our equilibrium expression, which means that we have to fill in absolutely nothing for the water. We don't care about its starting concentration, about its ending concentration, because it's inappropriate to talk about concentrations of water, period. So get rid of liquids and solids if they're in the reaction that you had to write. You don't need to fill in the ice chart for them. And then we can fill in the stuff that we do know. So the 0.20 molar solution of NH3, that's our initial concentration. We're starting at 0 and 0 for our products. For the change here for the ammonia is going to be minus X. It's a reactant. It's getting used up. It's going to be plus X and plus X for the products, because everything is in a 1-to-1-to-1. Products are created. They are made so that they are increasing in concentration. So for my equilibrium concentration, it's going to be 0.2 minus X, and I'm just going to go right ahead and say that's approximately 0.2, because my K value is significantly less than 1. It's on the order of 10 to the minus fourth or smaller. And then I have X and X. From this point, which is where I'm going to stop in this problem, you can see that we simply need to plug into our equilibrium expression using the value of the Kb that we know and solve for, in order to get pH, which is what we're looking for. But right here, right, X, that's what we're interested. X is your hydroxide concentration, meaning you take the negative log of your X value, you're getting pOH. You're not getting pH. Now, it's a super simple step to go from pOH to pH, but it is an additional step nonetheless. So you have to be mindful of that. So basically, that's how the Kb problem differs from the Ka problem. I'm hoping that you're seeing that there are some massive similarities there. I want you to think of them as similar processes. Essentially, you've got a slightly different start starting reaction, but then in terms of the pH work, it's virtually identical. You're just swapping out H plus for OH minus. And then the last one, using KSP to find solubility. I do want you have to feel very comfortable with KSP problems. They truly are no different than any other, but they tend to get a little funny sometimes with the units that they're looking for. So this question right here, we're going to be talking about units. The KSP for copper 2 azide CuN32 is 6.3 times 10 to the minus 10th. What is the solubility of CuN32 in water in grams per liter? The first thing that I want to address is what the question is asking for. It's asking for the solubility of this thing right here in a unit of grams per liter. Now, solubility is basically a way to discuss how much of something dissolves. The most common way we have of talking about how much something dissolves in a solvent is molarity, right? Molarity is our big unit of concentration. Well, what's molarity? Molarity is defined as moles per liter. Right. Solubility. You can talk about solubility as molarity. This question is asking for solubility, however, in grams per liter. I'm hoping that you see that there's an enormous relationship between molarity and then the unit that the question is actually asking for, and that we would go between grams per liter and moles per liter via gram formula mass. That's really the only conversion we would have to do. This is important for us because it means that instead of trying to solve directly for grams per liter, we want to solve for molarity. Then convert to grams per liter. That does actually say convert, even if the smartboard doesn't seem to think it does. And because that means that we want to solve for molarity first, that means that we can do an equilibrium problem, because equilibrium problems are all about molarity, right? We're using concentrations, we're using those square brackets. So the equilibrium problem here is appropriate. It's very appropriate. I mean, it says KSP is in the question. It's kind of given to us. But that's what we're going to be doing at the end. If we get the molarity, then we can convert that into the grams per liter, which is what the question is asking for. So I'm going to erase this, and we're going to start our equilibrium problem. 3 steps, always 3 steps. Step 1, write the reaction. What reaction are we writing? Massive tip-off given, KSP, which means we want to write an ion dissociation reaction for this thing. Now, this is probably a new compound to you. You probably haven't seen it before, but it's ion dissociation, so you're going to just do what you've done before. Ions dissociate. Now, what does it dissociate into? Well, the name of this thing is copper 2 azide, so that's really giving you a tip as to what the 2 ions are. They're copper 2 and they're azide. Looking at the formula, okay, well, it's copper 2. We know that it's got the copper charge of 2 because it says so in the name. And then azide. Well, what's azide? I guess it's this thing right here. It has to be. Subscript of this is 2, so I'm going to put a 2 out in front. And then it's N3. Now, how do I know the charge on the azide ion? Well, okay, the copper and the azide are in a 1-to-2 relationship. The copper has a charge of +2. Therefore, in order to cancel the charges, the azide has to have a charge of -1. So I'm using what I know about nomenclature to essentially work with a brand new ion, which is something that you would very much be expected to do. Great, I've written the reaction. Now we can fill in an ice chart. Right? That's always the process. Write a reaction, fill in the ice chart. Oh, there are absolutely no molarities given to us in the problem. And you know what? That's okay. Because this is a solid, this is aqueous, this is aqueous. And we do not include solids in our equilibrium expression, right? For KSP, we're used to having kind of no denominator, no reactants as a component of our KSP expression. And think too, we're never starting with any product unless the problem tells us, which means that our initial concentrations of the copper and the azide are both going to be 0. The problem does not indicate that there's already a certain amount of copper or azide in solution before we make this solution. Now we can sort of continue with filling in the rest of our ice chart. So even if you're not given any molarities, you can still fill in an ice chart. So we started with 0. Now we're going to do the change. Remember, products increase. So the copper is going to be plus X. The azide, here's where you have to be paying attention. The copper and the azide are in a 1 to 2 molar relationship, which means if copper increases by X, the azide increases by 2X, right? 1 to 2. You're always going to have double the amount of azide as will copper based on the chemical formula. That's huge. That's what those changes are based on, right? Changes are based on stoichiometry. So our equilibrium concentration of the copper is X, and the equilibrium concentration of the azide is 2X. We have now filled in the ice chart. It's looking a little scant, but that's okay. So we're going to go to our KSP expression. So I'm going to write the KSP expression for this reaction, just having a look at the reaction that we wrote. Remember, it's products of our reactants raised to their coefficients. So our products are the copper and the azide. The reactants is the copper 2 azide, but that's a solid, so it's not going to be included. So this is simply Cu2 plus times the concentration of the azide ion squared, right? Squared, because, you know, the coefficient is 2. So then we're going to simply plug in the values that we know. We know that the KSP value, going back to what it originally states, is 6.3 times 10 to the minus 10th. So 6.3 times 10 to the minus 10th is equal to, what do we write in our equilibrium line in our ice chart? We wrote X. And then for the azide, 2X. But we're squaring it. Don't leave that off. That's important. That's kind of like working with our rate laws. If you say to square it, you actually, you know, have to square it. Now I'm going to actually write this out a few more times, because I cannot tell you how AP Chemistry students are really smart about some things and really dumb about others. And this is something that you tend to be really, really dumb about. 2X as a value, if you square it, it is not 2X squared. You actually have to square everything that is on the inside of the parentheses, meaning it is 4X squared, and then multiply it by the X that's for the copper, and you get 4X cubed. I cannot tell you how sloppy and lazy students can get about this type of problem from this, basically from this exact point, taking X times 2X as a unit sort of squared, and then simply saying it's 2X cubed. It's not 2X cubed, it's 4X cubed. You make a dumb mistake like that and you're going to derail your problem, even though you know what you're doing. So be mindful of the algebra. So from this point on, you can solve for X. That's easy. When you do that, you get an X value of 5.4 times 10 to the minus 4th. Molar, this is molarity. Looking back to the ice chart, what does that represent? That represents the concentration of the copper ion. Now, we don't have to do a check on this because, look, we actually we didn't have to make any kind of assumption here. So, like, that's not going to be part of finishing this problem. Now, we basically now simply have to actually answer the question. The absolutely enormous point here is that the question, sort of, if we go back and look at it, it says, what is the solubility of CuN32? And we just solved for the solubility of the copper. What you have to realize is that we just got the molarity of the copper, and it's basically asking for the molarity of the copper to azide. These things are connected via coefficients. Coefficients are your best friend in the entire world, because it means if you know something about one thing, you can apply it to some information about something else. So because the copper and the copper 2 azide are in a 1-to-1 relationship, the molarity of the copper is going to equal the molarity of the copper 2 azide. That's critical to answering this question. You won't be able to answer that question unless you make that connection. You have to understand that in these KSP problems. If it's asking you for the molarity of the reactant, you can't solve for the reactant via the K expression. You're only solving for products and KSP expressions. But use the coefficients to go backwards to the molarity, from the molarity of the products to the molarity of the reactants. So I can state then that the CuN32 has a molarity of the same value, 5.4 times 10 to the minus 4th molar. Good. However, remember the problem wanted grams per liter. That's simple at this point. That's a matter of simply taking the moles and turning it into grams. Because, and I'm going to do this way because I do not believe in a molarity formula. I believe in a molarity definition. This is the definition of molarity, right? Moles per liter, 5.4 times 10 to the minus 4th moles per liter, and they want grams per liter. Okay, let's multiply this by something so that instead of moles on top and liters on the bottom, we have grams on top and liters on the bottom, and that's going to be the gram formula mass. So we're going to use the gram formula mass of the copper 2 azide, which, doing some math, is 147.6 grams per mole. You want units to cancel. You don't want moles on the top, you want grams on the top. So we're going to put grams on the top here and moles on the bottom. That way the moles are canceling out, and you're left with nothing but grams per liter. So this is going to be times 147.6 grams in 1 mole. Doing that math, we get 7.97 times 10 to the negative 2nd grams per liter, and we have answered the problem. The KSP problems tend to throw students for a loop. Don't let them. There's stuff that you already know that you simply have to apply. Apply stoichiometry. Apply that if you get the molarity of one thing, you can also know the molarity of something else, even if you didn't solve for it directly. Apply gram formula mass, going from molarity to grams per liter. Now, sometimes they'll just ask you for what they call molar solubility. If they ask you for that thing, molar solubility, in a KSP problem, simply know that they just mean molarity. So you build, Mrs. Julian can't spell, solubility. That's the exact same thing as molarity. But if they ask you for grams per liter, then you're going to have to go one additional step. So those are the examples of using K values to solve for concentration in specifically for Ka and KSP problems.